Hi everyone and welcome back to physics. This is Mrs. Hutchinson and today we're going to continue our discussion on motion. We're going to really focus though on accelerated motion and free fall. So accelerated motion, really what is accelerated motion? Well, let's define it. Accelerated motion is the rate at which the velocity changes during a given amount of time. Amount of time. So that is what accelerated motion is defined as. Now we also have constant velocity motion. So if you think about something in terms of constant velocity, is it accelerating? Well, if we're moving at, say, 55 miles per hour, and we're not changing it, we just set it on cruise control at 55, do we have acceleration? No. So constant velocity motion means that neither speed nor direction of an object changes, meaning we have no acceleration. Accelerated motion, however, on the other hand, is where either speed or direction of an object's motion changes. So yes, you can increase your speed or you can decrease your speed. That would be accelerated motion. Or you can turn your vehicle or make some kind of turns if you're running. So acceleration is defined as the rate of change in velocity of an object's motion. What that means is you're altering your velocity over a certain period of time. If speed changes magnitude, meaning the variable, the value, then the motion is accelerated. So here's our example. If we're going from 45 miles per hour, we're accelerating up to 55 miles per hour. Yes, we're experiencing acceleration. We are changing our velocity. If the direction of motion changes, then the motion is accelerated. So things that you also need to think about. Direction of motion, meaning if we're going in a straight line and we suddenly make a hard left, you kind of feel all these weird forces. Well, that's because you're undergoing accelerated motion. So going around a curve, or if you wanted to do a donut, if you will, that would be accelerated motion. Deceleration is also considered to be acceleration, but it is a negative acceleration. So say we're going from 55 miles per hour and we have to step on the brakes all the way down to 30 because, you know, we're in Pennsylvania and they just put speed limits up randomly, just I swear, so they can give you a speeding ticket. I might be a little bitter. I haven't gotten one yet, knock on wood. But anyway, 55 miles per hour, we decelerate to 30 miles per hour. It is a form of acceleration. It's just a negative acceleration. We do have a change in speed. So now, mathematically speaking, how can we describe acceleration? We can describe acceleration as a change in speed over a certain period of time. And you can find this equation on our reference tables. So taking a look at this, A is our acceleration, so it's just A equals V over T, change in velocity over our change in time. It's always final minus initial. So our units for acceleration are pretty simple. With physics, you have to be aware of the units that you're using at the particular time, and you have to give your final answer in the appropriate units. So if we take a look at plugging in our units for this equation, our units for velocity are typically meters per second, and our units for time are just seconds. So when we mathematically do that out, we would get meters per second, or meters per second like this. And when you see it mathematically written like this, you can just simply combine the two bottom numbers because of all the math. If you had to do it out, you would notice that that would happen. And you get meters per second squared. So our units for acceleration would be in meters per second squared. Our units for all of our velocities are meters per second, and our units for our time would be seconds. Okay. So a pretty simple equation, just a 3-variable equation, much like our velocity one. Velocity equals distance over time, acceleration equals velocity over time. And here is what the equation looks like on our reference tables. If you do not have your reference tables out, you will need them out for this particular unit or this particular video. So please make sure that you have them out. Flip to the mechanics section and you'll find this particular equation. I believe it's the second equation down. And again, here's what all of the variables stand for. So let's try an example using our new equation. We've got a tennis ball. It's dropped from a height of 14 meters. It starts out at rest and has a velocity of 16 meters per second when it hits the ground 1.7 seconds later. What was the acceleration of the ball? Let's write down all of our givens. Okay, so we know our distance is 14 meters. Okay, starts out at rest, has a velocity of 16.6 meters per second when it hits the ground, and 1.7 seconds later. Okay, so starts out at rest. That's actually an important statement. It's a hugely important statement. That tells us our initial velocity. If we're starting out at rest, our initial velocity is 0 meters per second. They then gave us our final velocity of 16.6 meters per second. And they also gave us our time, 1.7 seconds. Wanted, what are we trying to find? What was the acceleration of the ball? So that's what we're trying to find. So now the question is, well, what equation are we going to use? Do we have enough information to use just one equation, or do we have to use two equations here? Well, the two equations that we know are v equals d over t, and the other one we just learned of a equals change in v over t. Well, do we have enough information for a equals change in v over t? So remember, change in v equals final velocity minus initial velocity over our time. So, are we given final velocity? Yep. Are we given initial velocity? Yep. And are we given time? Yep. So we do not need our velocity equation. In other words, our distance has nothing to do with this particular problem. And you will find that in physics, you get a lot of information that you actually do not need to use to solve your problem. So please make sure that you are pulling out the important or pertinent information when you are solving for your final answer. So let's substitute in with our units. So we've got A equals 16.6 meters per second minus 0 meters per second all over our 1.7 seconds. Solving mathematically, you should get an acceleration of 9.8 meters per second squared. This 9.8 meters per second squared, you'll see, is actually quite an important acceleration. You'll see it very briefly in a couple of slides, and you'll note that it actually is the acceleration due to gravity, which makes sense since this tennis ball is in free fall. Let's try another example. Let's see if we can pull out the important information. In 2.5 seconds, a car increases its speed from 60 kilometers per hour to 65 kilometers per hour, while a bicycle goes from rest to 5 kilometers per hour. Which undergoes the greater acceleration, and what is the acceleration of each? So we've got a couple of things that we're solving for. First, we want to figure out, well, what's the acceleration of each of these? And, well, once we figure that out, we can figure out which one has the greater acceleration. So yes, the questions are asked kind of in a backwards way. It doesn't mean you have to solve them, as in which one undergoes the greater acceleration first, and then which one undergoes what is the acceleration of each second. You can solve for either one, whichever one makes the most sense as you're going. Let's go ahead and solve for our givens, or write our givens, I should say. We've got our time, 2.5 seconds for both. 2.5 seconds. If I can get that little point, there you go. The car, the initial velocity of the car is 60 kilometers per hour. The final velocity of the car is 65 kilometers per hour. The initial velocity of the bicycle, it says it starts from rest, so remember, if it starts from rest, our initial velocity is 0. And we can 0 kilometers per hour. And our final velocity is 5 kilometers per hour. Okay, so we've got all of our givens down, so let's solve for the acceleration of each one of these. So we've got several wanted. So we want to solve for the acceleration of the car. And we've got our acceleration of our bike. And then, which one's greater? I really tried to spell greater there, but it doesn't look like it. So you're just going to have to take my word for it. Okay, next, the equation that we're going to use. Well, it's a pretty simple equation. It's the one that we just learned. It's for both of them. It's our acceleration equals our change in velocity over time. So let's substitute in for both. So we've got a substitution for a car and substitution for a bike. So again, substitute with units, please, always. So final minus initial, kilometers per hour minus 60 kilometers per hour. Oh, I'm going to run out of room. 2.5 seconds. Our acceleration here is final, so 5 kilometers per hour minus 0 kilometers per hour over 2.5 seconds. We solve for both, and the acceleration turns out to be 2 kilometers per hour per second. That would be the unit looking at them. 2 kilometers per hour per second. And the other one for the bike is also 2 kilometers per hour per second. Didn't say we had to convert our units, so we didn't have to. So now we solve for the acceleration of each. Which one has the greater acceleration? They both have the same. Which makes sense. I mean, probably many of you already, just by looking at it, said, well, our car only increased by 5 kilometers per hour in those 2.5 seconds, and our bike only increased by 5 kilometers per hour in those 2.5 seconds. Therefore, they're undergoing the same acceleration. You would be correct. However, I wanted you to show me mathematically how you would solve for that. So now, we're going to learn a little bit about free fall. So free fall. Objects in free fall are accelerated by one force and only one force, that's our gravitational force. On Earth, this force is nearly constant with the following exceptions. As you get really, really close to the center of the Earth, super low altitudes, the force is slightly larger. As you get really, really far away from the center of the Earth, so super high altitudes, like way, 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 way up there, your force is slightly smaller. However, the average value of acceleration due to gravity is 9.8 or 9.81 meters per second squared, and this is symbolized by our variable g. Little g means gravity. Now, you'll see this, it's also given to you on your reference tables. I'm going to show you where in just a minute. But you'll also see that for many problems, it's very convenient to approximate the value of g to be 10 meters per second because it's super close to 9.8. We're only going to approximate it right on the next set of analogies, only because I like things to be exact. So, but I just want to show you how things kind of relate. Now, by convention, in case you didn't know, what goes up has to go down, and acceleration is a vector. So acceleration is a vector, which means that it has direction associated with it. That means that we have to identify the direction of positive acceleration and a direction of negative acceleration. So, an object with an upward velocity, meaning you throw a ball up, its upward velocity is positive. So let's say we threw it up with a positive velocity of 10 meters per second. It's being slowed by gravity because gravity always points down. Okay. So if we took our upward velocity to be positive, our acceleration due to gravity is then going to be negative because it's pointing in the opposite direction. An object with downward velocity is said to be negative. So as that ball goes up and it turns right back around, we now have a negative 10 meters per second velocity. The value of g is generally going to be taken at negative 9.8 meters per second. Of course, I'm going to show you how all of this kind of works relative to one another as long as you maintain an appropriate direction. As long as you're maintaining the direction in which you're doing something. If something's going up and you want to label it negative and you want to label acceleration positive, that's fine, as long as you are consistent. Let me show you where you can find your acceleration due to gravity. So if you flip to the very front of your reference tables, very front of your reference tables has the list of physical constants. You will notice the second one here has our acceleration due to gravity. The symbol happens to be little baby g, and it's 9.81 times 10, 9.81 meters per second squared. You can use 9.8, that's what I tend to use. But just in case you forget, which I don't think you will because we'll use it quite a bit. Let's take a look at our acceleration analogies. Pretty simple here. Your Aunt Minnie, who doesn't have a glorious Aunt Minnie? And especially check out how much money you're going to be raking in really quick. She gives you $10 per second for 4 seconds. How much money do you have after 4 seconds? Well, $10 per second after 4 seconds, 10 times 4 is going to give us, $40 in 4 seconds. Just, first of all, I just want you to think about, think about the logistics of this. You could make so much money. After 60 seconds, you're $600 richer. So I think personally, making $600 an hour is pretty impressive. But again, she only gave you $10 for the first 4 seconds. But regardless, I would say continue to charge that rate. If we take a look at how this kind of relates to free fall motion, a ball dropped from rest picks up speed at 10 meters per second per second. So this is our acceleration due to gravity. We're just rounding it for easy numbers in this instance. So after 4 seconds, how fast is it going? 40 meters per second. Because every second, it picked up 10 meters per second. So we've got our first second just 10 meters per second. Second one, it adds another 10 meters per second, and so on and so forth. So that's kind of how these two relate. Let's take a look at the next question. You have $20 and Uncle Henry gives you $10 each second for 3 seconds. How much money do you have after 3 seconds? Well, you start with 20. You then, for 3 seconds, are paid $10. So you should come out with $50. So first of all, I got to find some relatives that are going to be willing to pay off, as well as Aunt Minnie and Uncle Harry are. I said Henry, I think. But either way, regardless of whatever their names are, I like them. Now let's take a look. A ball, not a fall, a ball, let's change that, is thrown straight down with an initial speed of 20 meters per second. So here we go. We've got our initial speed of 20 meters per second. After 3 seconds, how fast is it going? Well, every second it gains 10 meters per second. So we've got 20 meters per second. After 3 seconds of gaining 10 meters per second, that ball now moves 50 meters per second. So again, that's kind of how these two relate. We started off at 20 meters per second, but then every second after that, it gains 10 meters per second. Okay, not too shabby. This is where you start to not like your aunts and uncles, but just take a look at it. It says here, you have $50 and you pay Aunt Minnie $10 a second. So she's starting to take money back from you, which I think is unfair because you're just a kid, right? So when will your money run out? Well, after 5 seconds, right? So we have to give her $50 or $10 every second. So after 5 seconds, we're back to being broke, which kind of stinks, really. It's uncalled for. However, let's think about this. We shoot an arrow up 50 meters per second. At 50 meters per second. Our acceleration is pointing in the opposite direction of 10 meters per second squared. So every single second, that arrow is slowing by 10 meters per second. So after 5 seconds, our arrow is going to have 0 velocity. Kind of how it works, right? So what will be the arrow's speed 5 seconds after you shoot it? Well, it's run out of speed, so 0 meters per second, because it lost 10 meters per second every second. So after 1 second, it went down to 40. After 2 seconds, it went down to 30. 3 seconds is 20 meters per second, and 4 seconds, it's down to 10. After 5 seconds, it's down to 0. So that arrow is literally without velocity after 5 seconds. What will be its speed after 6 seconds? So we've got our arrow moving up at 50 meters per second. Once it reaches that peak here, its speed is 0 meters per second. So that's after 5 seconds. Is it just going to hang out there? Heck no. I mean, it would be awesome, but then we would have like a sky full of just random objects, which would be kind of cool. So what it actually is going to do is it's going to turn around and fall back down to Earth. So after it started from rest now, we're going to disregard that section for now. It started at rest, and it fell for 1 second. So how fast does it go after 1 second? Acceleration due to gravity, 10 meters per second squared. So after 6 seconds, it's moving 10 meters per second. After 2 seconds, it's moving 20 meters per second. Kind of cool. 3 seconds is 30 meters per second, and so on and so forth. So after a round trip of 10 seconds, it's going to be back to its original speed. And if you shot it straight up, it'll be right back to its original location. So let's do some practice problems. An object is dropped from rest at the top of a tall cliff. How fast is the object going after 1 second of free fall, after 2 seconds of free fall, and so on and so forth. So this table below deals with the problem above. So here we go. We've got our object. It's starting at rest, so our initial velocity is 0 meters per second, starting from rest. So at time 0, we're moving 0. After 1 second of free fall, if we're going to round, let's just do easy numbers, rounding easy numbers. So let's call our acceleration due to gravity negative 10 meters per second squared. Because again, when you move up conventionally speaking, that's our velocity being in the positive direction. If we move down, conventionally speaking, our velocity is in the negative direction. Okay. So as we're going down, what is our instantaneous speed? Well, we've gained 10 meters per second, so negative 10. After 2 seconds, total, negative 20, negative 30, negative 40, negative 50. Again, as long as you're maintaining the same convention, the same directions. So if you wanted to make, so we've got our X and Y directions. If you wanted to make going up be negative and going down be positive, as long as you are consistent, works for me. Okay. So that's the end of this particular video. So I am going to see you for our next video.